All right, we are at the last section, 32.8, uh, and it's the transformer and power transmission. So let's share the PowerPoint. I don't think I'll be going to the iPad for any of this. It's all pretty straightforward. Um, so if you recall, uh, for economical use of high uh, voltage and low current transmission of power, um, to minimize the I squared R loss, the lines are commonly uh, high voltage lines, 350 kV lines. In some areas, even use 765 kilovolts. At the receiving end, the it requires power at a low voltage, so the voltage is decreased to about 20 kilovolts, 20,000 volts at the distribution station, then to 4,000 volts for the delivery to residential areas, and finally to 120 volts and 240 volts at the customer site. So the transformer is the device that can change alternating current and current without causing appreciable changes in power delivery. So in the figure is a typical transformer in a residential area. Um, so the let's read the caption on the figure. An alternating voltage delta V1 is applied to a primary coil, and the output voltage delta V2 is across the resistor of resistance RL. And you had experience with this with the little solenoids that you had, and you know that in order to increase the induced current on the secondary side, you put an iron core into the center of uh, into the center of the uh, the coils, the uh, that that increased the magnetic permeability inside the solenoid. That was the word I couldn't think of. Inside the solenoid to increase the permeability and increase the current uh, in the secondary side. So delta V is the supply side. So delta V equals minus the number of turns in N1 times dphi dt, the magnetic flux. And since it's alternating current, it's always changing. So there's always a magnetic flux going through the coils. So the delta V1 is the supply side, and delta V2, we're going to assume that all of the flux that goes through the iron appears on the secondary side. So the delta V2 is equal to minus N2 d phi dt of the secondary side. It's the same flux. We're assuming that all the flux goes through, and it's got the load resistor on the other end, so that delta V2 is equal to N2. The delta V2 is equal to N2 um, divided by N1 times delta V1. So if N2 happens to be greater than N1, the output voltage V2 exceeds the input voltage, and this is called a step-up transformer. So it'll step up the voltage. Um, and if N2 is lower than N1, the output voltage is less than the input voltage. This is a step-down transformer. This is what you have in most, your phone chargers. If you still the type that plug it into the wall, it has a transformer to step it down, um, step down transformer. And here is the circuit diagram for transformers connected to a load resistor. You have the current in the primary side and the current in the secondary side. The two vertical bars right here represent the iron core. So this is how it looks in a circuit. Now the primary winding in this transformer is attached to the prongs of the plug, whereas the secondary winding is connected to the power cord uh, on the right to power your device. You plug it in, it most likely steps down. Your typical value is 12.5 12.5 volts to step it down. Um, the now you can get a lot of eddy current losses in these transformers. So quite often, if you've ever seen a transformer, you'll see that it's made of laminated plates, and that reduces the eddy current losses. And we can get anywhere from 90 to 99% of the flux that goes through the primary goes through the secondary coils. So they can be pretty efficient. Um, so the I delta V1 equals I1 delta V1 equals I2 delta V2. So it's not a free trade-off. In other words, uh, you may get you with the lower voltage you get um, increased current, but you'll see I1 delta V1 is power 1, and that equals I2 delta V2 equals power 2. So the power is the same. You can't multiply the power. Um, so I2 is equal to V2 delta V2 divided by RL by the load. So I1 is equal to V1 divided by the equivalent, and the R equivalent is equal to the number of turns N1 divided by N2 squared times RL. So this is actually used to do what is called impedance matching. For an example, a transformer connected to a 1 kilovolt output of an audio amplifier and the 8-volt speaker ensures that as much audio signal as possible is transferred to the speaker. So you can do impedance matching using um, the transformer. It's often used in that way. Um, okay, I think. Well, I already did that one, right? The R equivalent is equal to N1, N2 squared times RL. I must have hit the back button. And that's it for this chapter.